All right, so before we move on to intersection of planes, which I like to do in a separate unit whatsoever, or completely, because it is really messy to picture, we're going to look at a Cartesian or scalar equation of a plane. We did Cartesian or scalar equations of lines. That was y equals mx plus b, or ax plus by plus c equals 0 in standard form. There is no such thing as symmetric equations of planes. There was vector equations where you needed a point and two direction vectors. You could turn that into a parametric equation, but it is not possible to turn it into a symmetric equation. It is possible to have a Cartesian or scalar equation of a plane in 3 space, because planes happen in 3 space. So first of all, we have a definition. And it is that there's this thing called a normal vector. Now, you've done normals already, and they're in calculus, and that was perpendicular to the slope of the tangent. Orthogonal is another word for normal. 90 degrees is another word for normal. Perpendicular is another word for normal. So a vector that is perpendicular to a plane, and therefore is perpendicular to every vector in that plane, so every line that's drawn on this plane that has an arrow on it, so every vector on this plane is going to be perpendicular to this normal vector. So normal vector is like you placing your pencil on your desk so it sticks straight up at 90 degrees, because your desk is a plane. That's where you place a piece of paper, which is a plane. So a plane can actually be described using the normal vector and a point. So you don't always need 2 direction vectors and a point. 2 direction vectors and a point makes a vector equation, which turns into parametric equations. But if you want a Cartesian or scalar equation of a plane, then all you need is 1 perpendicular, i.e. normal vector, and 1 point. So the plane passing through the point P, 1, x1, y1, z1, and having a normal vector that has components A, B, and C, actually has a Cartesian or scalar equation of the form ax plus by plus cz plus d equals 0. So it's very much like the standard equation of a line, but it's a Cartesian equation of a plane. And d is defined by this formula, which I never use, and I will show you how I never use it in the question that's coming up. Before I start to talk about how to solve this question, I'm going to read it and tell you about this little symbol. So it says, given that the plane, and you've got the pi symbol, passes through the point P, 5, 7, negative 2, so we have a point, and has a normal vector equals A, capital A is 3, capital B is negative 6, capital C is negative 1, determine the coordinates of 2 other points on the plane. So the first thing I want to mention is this is your short form for line, and the pi symbol is the short form for plane. I did not make that up. The second thing I want to scribble is that that's A, that's B, and that's C, because we are given a normal vector. So when I dig out the form of a Cartesian equation of a plane, the first thing I get to do is I get to put the 3 in here, the negative 6 in here, the negative 1 in here, and my d remains unknown. And if you want to know your d, you can totally use this formula. But I'd prefer to use algebra, because I have a point where this is my x coordinate, this is my y coordinate, and this is my z coordinate. And I can put those in, and then I'll only have one unknown. So I'll have 3 times 5 minus 6 times 7 minus negative 2 plus d is equal to 0. So if you take a look at the formula, it's saying put x1 in for the x, put y1 in for the y, put z1 in for the z, and then haul it all over to the other side so it's the negative version of it. What I'm doing is manipulating math in a very grade 9 way, which I'm much better at than memorizing formulas. Don't know where that came from. So 15 minus 40 plus d equals 0. And come on, it's Sunday. Give me a break. 15 minus 40 is equal to negative 25. So therefore, the Cartesian or scalar, because these are all scalars, not dependent on a vector, Cartesian equation of this plane is our a, x, our b, y, our c, z, plus the 25, which is our d, equals 0. And now we can go on and answer the rest of the question, which is to determine the coordinates of two other points on the plane. So something other than 5, 7, negative 2. And we can do that in any way we like. So I like to think about this a little bit to minimize my work. So I can sub in any x and any y and any z as long as I create a 0 on the left-hand side to make a 0 on the right. So as long as this turns out to be 0, then I've made a point. As in, as long as I select an x value and a y value and a z value that makes this true, it's on the plane. So I could sub a value in for z and sub a value in for y and then solve for x to make it work if I really wanted to. Or I could sub a value in for z and sub a value in for y and x and solve for y to make it work. Or, because my z has a 1 in front of it, I could sub a number in for x and y and solve for z, and it's going to give me less work. So I like to minimize my work. And I also like to pick numbers that don't create problems for me. So I'm going to let x is equal to 0 and y is equal to 0. There is nothing wrong with that because I have already guaranteed that it's not this point, because this point doesn't have 0, 0. So 3 times 0 minus 6 times 0 minus 7 minus z plus 25 is equal to 0. So it's 0 minus 0, which is 0. 25 is going to get left behind on the left. Z is going to cross over to the other side. And I get a point 0, 0, 25. That's one of the points. That was an easy one. Now all I have to do is make a second one, because it says determine the coordinates of two other points on the line. So I can't pick 0, 0 again. So I'm going to pick 1, 0, or 1, 1, or 0, 1. So I already know that my point is 0, 1, something or other. I just need to see that last blue line. So 3 times 1 for x minus 6 times 0 for y minus z plus 25 is equal to 0. So that's 3 minus 0 plus 25 is equal to z on the other side is positive. 3 minus 0 plus 25 is 28 equals z. And this may be a completely different answer than is sitting in my note that's on the Google site. And the reason is I'm in a different mood. I'm picking different x and y values. And you could too. If you really wanted to punish yourself, you could use x is 117 and y is negative 42. And then you're going to have to dig out your calculator. I've decided I don't want to do that. So, next question, last question for this note, is determine the Cartesian equation of the plane that passes through those set of points. So, unfortunately, I have no normal vector. I have 3 points. I could pick one, but I have no normal vector, and I need a normal vector to do a Cartesian equation. So can you figure out how to find a normal vector? Can you figure out how to have a vector that is poking out of the piece of paper with those 3 points on it? Here's how you go about it. You need a direction vector. So I am going to make direction vector AB, as I almost always do. There it is. I need a second direction vector. I'm going to find AC, as I almost always do. This one I'm going to tidy up. Technically, I guess I could tidy this one up too. Meaning I could change all the signs, so I've scalar multiplied this by -1 in both cases. So now what I have as a picture, a bad picture, is I've got a plane, I've got 3 dots, I found out this direction vector, and I found out this direction vector. And what I need to do is I need to find a vector that is poking up through this page at a 90-degree angle. So basically, I need a vector that is 90 degrees to both of those two. Well, guess what? That is the definition of the cross product. A vector perpendicular to 2 other vectors. So I am about to do the cross product between the 2 vectors I just found, and that will give me the normal. So that means a whole bunch of scribbling. Doesn't matter which order I do it in. So 1, 6, 0, 1, 6, 0, 1, 10, 1, 1, 10, 1, scribble, 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 scribble. Down to the right, minus down to the left, down to the right, minus down to the left, down to the right, minus down to the left. So I end up with 6, -1, 4, and that is my normal. Pause for a sec. Sorry, got a text, thought it was important. It was not. All right, so now what I have is I have the start of my Cartesian equation. So AX plus BY plus CZ plus unknown D is equal to 0. And what I need to do is I need to pick one of these points to sub in there, and regardless of which point I use, I should get the exact same D value. So I am going to pick, it's a toss-up. I kind of want to pick this one because I like the number 1, but I also kind of wanted to use this one because that means I don't have any Z's to worry about. I'm actually going to pick that one. So 1, -3, 0. 1, -3, 0. 1, -3, 0. 1, -3, 0. You were going to let me get away with this, weren't you? So 6 plus 3 plus 0 plus D is equal to 0. So that's 9 plus D is equal to 0. So D is equal to -9. And that means, therefore, the Cartesian equation is 6x minus 9 plus 4z. 6x minus y plus 4z minus 9 is equal to 0. Now, in case you didn't believe me, remember the other choice that I was going to pick was 1, 1, 1, just based on easiness. So in case you don't believe me, let's take this and sub in 1, 1, 1. Let's see if we get the same D value. Oh, we do too. I did not lie to you. See, I'm no liar. Not intentionally, anyhow. Okay, so the last thing I want to talk about is just the name of something. Something that we did here, where we took the cross product of two vectors and dotted it with something else. And that process, when you cross product two vectors and dot it with something else, is called the triple scalar product. And the triple scalar product is a rule. This is the triple scalar product. This is the result of the triple scalar product if your vectors are coplanar, meaning if your vectors, that last one is really bad, it looks parallel to this one, but if your three vectors lie in a plane, as opposed to, I don't even know if I can draw this. And then this one is like sticking out, but not necessarily at 90 degrees. So this is coplanar. This is non-coplanar. Two are coplanar, but the third one is not. So if you want to check for something being coplanar, this is the rule with the result. So that actually works well with this particular question that we did yesterday, whenever you did it. That is, you took the two direction vectors and you dotted it with a known point on the plane and the point that you were testing to see, are these three vectors, the two that you know are in the same plane and a third one, to see if it equals 0, and we ended up not. So if you need to review that, that gives you a reason for this even existing. But other than that, here are the suggested questions. Again, not split into R2 and R3 because planes do not exist in R2.